The objective of this video is to understand the reaction quotient and equilibrium constant in a reversible process. If we want to define things like reaction quotient or the equilibrium constant, we must have a reversible process, either a chemical process or a physical process. Now, this reaction quotient and equilibrium constant, they are both actually a ratio, concentration ratio of products to reactants. Let's say we have a hypothetical reaction or process. You have the two reactants, and then you have the forward process and the reverse process. You have the products. And think these simple letters as the stoichiometric coefficient. So how do you write this expression for reaction quotient Q? That is the ratio between product concentration and reactant concentration, and we also consider the stoichiometric coefficient. Your numerators are going to be the product concentration, and you have the stoichiometric coefficient. And if you have any other products, list them all and then put the stoichiometric coefficient, and then you list the reactants as the denominator. So that is how we write the expression for reaction quotient. And this reaction quotient is the ratio of products and reactants of any reversible process at any point of the reversible process. So that means as long as you have a reversible process, you can write reaction quotient expression. However, when it comes for the equilibrium constant, having a reversible reaction is not enough. The process must be at equilibrium if we are to write the equilibrium constant expression. So by now you know what equilibrium state means. The forward and reverse processes, the rates must be equal. The point where the forward and reverse reaction rates are equal is the point where there is equilibrium. It's only for the equilibrium point that you can write KEQ. Compared to that, the reaction quotient Q can be written to any point. It can be a point where the reaction rates equal, or it could be a point where the forward reaction is fast or the reverse reaction is slow. So Q can be written for any point, whether it is forward reaction is faster and reverse is slower, or the forward reaction is slower while the reverse is faster. So Q is something that can be written at any point, but reaction quotient is only for system at equilibrium. All right. Now let's see how this Q and KEQ can relate. Now, in a previous video, I mentioned why any system want to achieve equilibrium. Equilibrium results in stability. So that means everything ultimately like to achieve stability. So that means this Q will eventually try to reach the KEQ. Why? The moment these reaction rates become equal, system comes to an equilibrium. At the equilibrium position, if you write this expression, it automatically becomes KEQ. So let's say if you have the equilibrium constant at the equilibrium position, this Q is same as KEQ. And there can be other two possibilities. One other possibility is that you have a small q. let's say a small q. What does it mean by a small q? If you write this expression for q, the ratio between products and reactants, and if this ratio is actually smaller than KEQ, Q is smaller than KEQ situation. If you are having a small number for the Q or the reaction quotient, what does it mean? If you are to get a smaller number as the answer for this ratio, that means you should have more reactant and less products. So that means small q means you have more reactants and less products. That kind of a ratio will result in a smaller q. If you are going to have more reactants, that means reaction can actually go forward. Why? You have more reactants, they can collide with each other and make more product. So if you end up with very small q or a q smaller than the defined equilibrium constant, that actually means the system prefers to move forward. So q, a smaller q value can signify the system favors the forward reaction. On the other hand, let's say if you are going to have a large q, meaning if your q is larger than KEQ. If you're having a large q, what does that mean? You have more products and you have few reactants. If that is the case, and by nature things prefer the stability, stability is where the Q equals EQ, the system try to seek the stability by reaching equilibrium or by trying to equaling this Q to KEQ. So that means the system will try to arrange itself to reach equilibrium. What does that mean? The reverse reaction is favored. So that is what meant by this Q signifies the direction of the reaction. If you have a very small reaction quotient, that means the reaction will favor the forward reaction. And if you're going to have a very large reaction quotient, it will favor the reverse process by breaking down the products into reactant. So that is one way how we can show how reaction quotient is going to relate to equilibrium constant. So this signifies the direction of the reaction. However, when it comes for equilibrium constant, since we are writing the equilibrium constant for a system at equilibrium, what this equilibrium constant signifies is not the direction of the reaction, it rather signifies the position of the equilibrium. Remember, equilibrium is where you have the rates equal, forward and reverse is equal. There is no favoration, but the position can be shifted either into product direction or into the reactant direction. So let's look at a perfect condition. Is there a perfect condition that K becomes KEQ becomes 1? If you have equal product concentration and reactant concentration, if you have equal numbers in this ratio, what will be the result? For example, think numbers. If you divide 10 by 10, what will you get? You get 1. So that means if your ratios, the product and reactant ratios are in the equal amounts, you will achieve this KEQ equals 1 situation. And then you can find the other two extremes where you have the KEQ going to be larger than 1 and the other situation where equilibrium constant is going to be smaller than 1. Now again, let's think with numbers. If you are to achieve an equilibrium constant which is larger than 1, what kind of numbers can you think of? If you divide 10 by 1, what is the answer? Your answer is 10. So that means you have what? More products and less reactants. So this situation, an equilibrium constant larger than 1 signifies that the equilibrium is positioned towards more products. So this means positioned towards products. That means when the system is at equilibrium, what you have is more products. If your equilibrium constant is less than 1, for example, situation like 1 divided by 10, that is 0.1. Now this is a situation that signifies what kind of a situation? This means less products and more reactant. So if you are getting this kind of a equilibrium constant smaller than 1, what it signifies is that you have more reactant when this system is at equilibrium. In other words, when the forward and reverse reaction rates are equal, if you have more reactants, your equilibrium constant will be less than 1. When the forward reaction and the reverse reaction rates are equal, in that situation, if you have more products, then your equilibrium constant signifies that you have more products at equilibrium. So that is the main differences between the reaction quotient and the equilibrium constant. To sum it up, the reaction quotient is defined for any position for any reversible reaction. For equilibrium constant, your reversible process must be at the equilibrium. The Q, or the reaction quotient, signifies the direction of the reaction, while the equilibrium constant signifies what is more prominent at equilibrium. Is it products that you find at a higher concentration, or is it reactants that you find at higher concentration?